Assalamu alaikum. Bismillahirrahmanirrahim. Today we are going to start chapter 5. In the past we read chapter 2, 3, 4, and during these chapters we were able to develop uh, equilibrium systems for two-dimensional, three-dimensional equilibrium forces, different joint techniques. Then chapter 4 we talk about trusses. Now we are going to focus on forces, how they are treated and how they are supposed to behave in real time. Now, if you remember, in the previous chapters, we treated all forces as concentrated along their lines of action and at their points of application. This treatment provides a reasonable model for those forces. Actually, concentrated forces do not exist in exact sense, since every external force applied mechanically to a body is distributed over a finite contact area, no matter how small the area is. The force exerted by the pavement on an automobile, for example, on an automobile tire, is applied to the tire over its entire area of contact, which may be appreciable if the tire is soft. When analyzing the force acting on the car as a whole, if the dimension B of the contact area is negligible, as you can see in the figure right here, the dimension B is negligible compared to the other permanent dimensions such as the distance between wheels and other, then we may replace the actual distributed contact forces by a single resultant R, treated as a concentrated force. Even the force of contact between a hard steel ball and its race in a loaded bearing, as you can see in the figure, is applied over a finite area, though extremely small contact area. The force applied in a two-force member of a truss, as you can see here, the applied over actual area of contact is through a pin joint against the hole and is internally across a cut section. As you can see here, it is spread over a pin joint like this. It's a simple cut section. Now, in these and other similar examples, we may treat forces as concentrated when analyzing their external effects on a whole body. If, on the other hand, we want to find the distribution of internal forces in the material of the body near the contact location where the internal stresses and strains may be appreciable, then we must not treat the load as concentrated but must consider the actual distribution. This problem will not be discussed here because it requires knowledge of materials which belongs to more advanced levels. When forces are applied over a region whose dimensions are not negligible compared to other pertinent dimensions, then we must account for actual manner in which the force is distributed. The summing effect of the distributed force over the entire region using mathematical integration, this requires that we know the intensity of the force at any location. There are three categories of such problem, how they are distributed. Number one, line distribution. When a force is distributed along a line as in a continuous vertical load supported by a suspended cable, as you can see in figure A, the intensity W of the load is expressed as force per unit length of the line, newtons per meter or pounds per foot. The second is the area distribution. When the force is distributed over an area, sorry about that, we have to start again. I'm sorry. I'm going to talk about the second area distribution. When a force is distributed over an area, as with the hydraulic pressure of water against the inner surface of this section of a dam, now in case of dam, the intensity is expressed as force per unit area. The intensity is called pressure. For the action of fluid forces and the stress of the internal distribution of the forces in solid. You have the basic knowledge of Pascal's law. However, uh, in kilopascals, you are familiar with the pressure force per unit area in pound per inch square. Now, the third type of load distribution is the volume distribution. A force which is distributed over a volume of a body is called body force. Now, the most common body force is the force of a gravitational attraction which acts on all elements of mass in a body. Determination of force on the support of heavy cantilevered structure, as you can see in the figure C, for example, would require accounting for distribution of gravitational forces throughout the structure. The intensity of gravitational force is the specific weight, where rho is the density and g is the gravitational due to gravity. Then rho g are, kilogram per meter cube and meters per second. As you can see, the body force due to the gravitation attraction of Earth is by far the most common encountered distribution forces. As you can understand, you all experience this thing. Now, what we have here is simple how these forces are categorized. So let's talk about the center of mass and centroids. What is a center of mass? Now let us consider a three-dimensional body of any shape, any size, having a mass m. Now if we suspend the body as shown in the figure right here from any point such as A, the body will be in equilibrium under the action of tension in the cord and the resultant W, that is under the action of gravitational force field. This force field is acting on all the particles in the body. Now, the resultant is clearly collinear with the cord. Assuming that we mark assume so let us mark this line of action by which this hypothetical hole and this of negligible size and over which this cord is acting, and straight line down towards the center of the earth. Now we repeat this experiment suspending the body from other points such as B's and C's. In each instance we mark the line of the action of the resultant force. For all practical purposes, these lines of actions will be concurrent at a single point G, now which is called center of gravitational body. An exact analysis, however, would account for the slightly differing directions of the gravitational force of various particles of the body. Because of those forces converge towards the center of attraction of Earth. Now, because the particles are at different distances from the Earth, the intensity of force field is not exactly constant over the body now. But this is of no practical importance as long as we deal with these bodies whose dimensions are small compared with those of Earth. So, assuming a uniform and parallel force field due to the gravitational attraction of the Earth, this assumption results in the concept of unique center of gravity. So, how do we determine the center of gravity? To determine mathematically the location of center of gravity of any body, we can apply the principle of moment. Now, as you have studied in chapter 2, parallel system of gravitational force field, the moment of a resultant gravitational force field about any axis equals the sum of moment about the same axis of the gravitational force field dw, as you can see right here in this figure. Uh, the resultant of gravitational force field acting on all elements of the weight of the body and is given by the sum of the W, defined as, that is, adding all the small dw's together, and we apply the same moment principle about y-axis. For example, the moment about x-axis of the elements is x dx, then the sum of moment about z-axis would be z dx. Now we have to understand that the sum of moment must equal x W times x prime. Now x prime is the mean value, the center value. Now with similar expressions for the two other components, we may express the coordinates of center of gravity as x prime integral, that is integrating all the small weights about with the distance x from the from the corresponding y-axis, and distance y from the corresponding y-axis, and distance z along z-axis, and we can find these moments and divided by the actual weight to the center mass, we can find this mean position along x prime, y prime, z prime. Now to visualize the physical moment of the gravity force now to visualize the physical moments of the gravity force appearing in third equation, we may reorient the body and attach axis to the z-axis in horizontal. Now it is essential to recognize that the numerator of each of the expression is the sum of the moments. Yeah, that is important. Whereas the product of w and corresponding coordinate g represents the moment of sums. This moment principle finds repeated use throughout the mechanics. Uh, Now, students of this class, remember that I gave them a project. Now, this is one technique you can use to find the centroid of your system, which will be choosing for your project. Now, let's carry on. With the substitution of W is equal to mg and dW is equal to g, as g is constant, dm small mass, the expression of the coordinate of the center of gravity becomes x prime is equal to integral x over dm over m, y prime is equal to integral y dm over m, and z prime is equal to integral z dm over m. So equation 1b may be expressed in vector forms with the aid of 4 by 5b, in which the elemental mass and the mass center G are located by their respective positions r xi and yj. R is equal to xi plus yj plus zk, and the corresponding center is at r prime, defined as x prime I plus x prime j plus x prime k, where r is the any position of dm. So this can be given as r prime is defined as right here, r is equal to integral r over dm over m. Now the density of the body is its mass per unit volume. Thus the mass of a differential element of volume dv becomes dm is equal to rho dv. If rho is not constant throughout the, you can say, body, but can be expressed as a function of coordinate of the body, we must account for this variation, and can be calculated using when calculating the numerator and denominator of this equation right here. So it can be expressed as, so rho is become function like right here, putting it in this equation, and what you get is this thing. Now it is not out of the integral, as we know that the rho is varying with mass throughout the system, so it is important. The center of mass, now we have two things we have studied so far, the center of mass and center of gravity. So how do we differentiate between the two things? Now in the last three equations we see that they are independent of gravitational effect. Since G no longer appears, they therefore define a unique point in a body which is solely the distribution of mass. This point is called center of mass, and clearly it coincides with the center of gravity as long as the gravity field is treated as uniform and parallel. This means if you are within the Earth's field, the gravitational field is almost constant and the size of the object is very small. It is meaningless to speak of the center of gravity of the body which is removed from the gravitational field of the Earth, since no gravitational force would act on it. Now, in most problems, the calculation of the position of center of mass may be simplified by an intelligent choice of reference axis. In general, the axis should be placed so as to simplify the equation of the boundaries as much as possible. Polar coordinates will be useful for bodies with circular boundaries. Other important clue may be taken from the consideration of the symmetry of the body. Whenever there exists a line or a plane or symmetry in a homogeneous body, a coordinate axis or a plane should be chosen to coincide with this line of plane. The center of mass will always lie on such a line or plane, since the moment due to the symmetrically located elements will always be cancelled by each other, or you can say mass distribution on either side. The center or mass G of a homogeneous right circular cone will lie somewhere on its central axis, which is the line of symmetry. The center of mass is above of the right half circulated cone lies in the plane of symmetry, as you can see in figures A and B. The center of mass of a half ring, as in figure C, you can see lies on both of its plane. It's right in the center by a symmetric axis right in between.